Welcome back, ladies and gentlemen. We're going to take one more look at another one of these solids of revolution problems. This is solids of revolution part 3. And let's take a look at what we are going to be finding the volume of. We're going to use integration to find the volume of a shape. Let's take a look at this shape here. So we're going to have a shape bounded by the square root of x, and what else? By the line 1/10 x, and by a vertical line x equals 4. So these three lines together enclose a space, a region. This region is going to be rotated around the x-axis to make a three-dimensional figure. And we are going to use integration to find the volume of this three-dimensional figure. There's the region, and this shape you can see there, it's sort of like an old-fashioned headlight or something like that, but it's got this piece in the middle missing. Here's a cross-section, and the cross-section is a washer. And so we're going to use the washer method. Let's see if this video does anything else interesting. That was pretty interesting. Absolutely. So let's take a look at how we might do this. First, I'd like to show what this square root of x graph is going to look like. So from 0 to 4, from x equals 0 to x equals 4, if we rotate this, we're going to get a shape. Let's do it on medium. Boom. So that's the shape we're dealing with on the outside. Now, the shape on the inside is determined by this line. This is x over 10. Let's refer back to the original video. So there is the original square root of x graph. Here comes the graph 1/10 x. And what we're going to do is get a volume that is a result of subtraction. We're going to take the big blue outer shell, the shape right here, and we are going to subtract this guy, little cone in the middle there. So that cone has been removed, and you can see that pretty well in the video right around there. There's the whoops. So there's the inside. You can see that kind of inside cone. That's this guy right there. That's what we're going to be removing. So we're going to be subtracting this shape from that shape is essentially what we're doing. But we're going to also think about this in terms of the washer method. So let's think about this shape as an accumulation of circles, but circles with the middle missing. So for instance, let's try to visualize what this cross section would look like. So it's about at 2.5. So if we rotate it, it's going to go down to negative 2.5. So if we rotate this thing around the x-axis, we are going to get a washer. That middle part is going to represent the missing inside. Here's another washer here, and in this particular problem, the outside circle of the washer gets larger, and the inside circle is also getting larger. Each of these circles is defined by its own unique function. But the premise is still the same. We are accumulating washers, and we are accumulating washers from x equals 0, which is right here, to x equals 4, which is right here. So we need to define the area of one of these, or any of these washers, really. So let's take a look, for example, at the washer at x equals 4, the biggest washer on the outside. So that washer has this general shape. It has an outside circle, and it has a smaller inside circle. The area of this is just this part. Now you can define the area of this circle as the area of the larger outside circle minus the area of the smaller inside circle. So that's going to be pi r squared minus pi r squared. or pi big R to represent the larger radius, pi big R squared minus pi little r squared, or you can factor out the pi, the common factor, and just write it like this. So let's take a look at that last circle. The last circle's radius starts at the x-axis and extends all the way up to the upper graph. The upper graph is the square root of x. So this is at x equals 4. So the distance from the x-axis to that point is the square root of 4, which is just 2. We could pick any arbitrary place in the middle of this graph and use the same logic. So here's just a random circle, a cross-section somewhere in the middle, and it's just at x equals x. Doesn't matter what it is. This is at some random x. So the length, the distance of this larger radius is the square root of x. So far, the area of this washer is going to be pi times the square root of x squared minus little r. Well, little r is simply the distance from the x-axis to the smaller, the lower of the two graphs. That graph is the linear function x over 10, 1/10 x. So at x equals 4, for instance, this small length right here is 1/10 of 4. You just plug in whatever value it is. For some random value of x, the distance of the length of little r right here is going to be 1/10 of whatever that x value is. So this washer, that's right here. Boom. So that's 1/10 of x, and the big one all the way to the outside, that is the square root of x. So let's go back to our washer formula. We have pi times big R squared minus little r squared. Little r is 1/10 x. We square it, and this is the formula of a washer. So we are going to accumulate all the washers made by these two graphs from 0 to 4. The pi comes out. If we square the square root of x, we just get x. If we square 1/10 x, we get 1/100th x squared. And if we do the first step of the fundamental theorem of calculus to actually define this volume, the pi comes out, we get x squared over 2 minus, it's x to the third over 3 multiplied by 1 over 100. That's x to the third over 300 from 0 to 4. I'm not going to finish this. You would simply plug in a 4 and then plug in a 0, subtract, and that ends up being the volume of this guy right here. Let's see if I can find it quickly. Boom. That guy. Well, not that guy. That guy. That's a better picture. So that's it. That is the washer method. But it's a little more involved problem. Thank you, and goodbye. And wait a minute. I gotta make sure I'm writing this properly. What did I leave out, ladies and gentlemen? It may seem insignificant, but it is, it's important to take care of the details. I am, in fact, integrating with respect to x. That's all for now. Goodbye.